Okay, hello everyone, and thank you for joining us. This webinar is organized by IEEE Ottawa AP MTT chapter in collaboration with other sections, chapters, and affinity groups within IEEE. This webinar is titled Antenna Design Life Cycle, and the speaker is Gopinath Gampala. Gopi is a manager in the global technical team with Altair. He holds a B.Tech degree in Electronics and Communications Engineering and a Master of Science degree. He has been working in the field of CAE for the past 15 years. Before passing on to Gopi, I would like to introduce Dr. C.J. Reddy, who would like to give a short introduction before we start the webinar.
Very good. Thank you very much, Mo, for the introduction and also organizing this talk. I mean, of course, I'm not going to take too much time. I just want to say that, currently I'm serving as the 2025 APS President-elect, Antennas and Propagation Society President-elect, and it's an honor for me, I think, to serve the society. Plus, we also have Dr. Javed Siddiqui, who is the chair of the site committee here. I see that there are a lot of students in this group, so I just want to show you something that would be of interesting to you. If you're not a member of APS, and if you're a member of IEEE already, not a member of APS, I strongly recommend that you become a member of APS by just $1 US dollar, I guess you can become. You can scan this QR code, which will take you to the page where you can sign up. And as you can see, APS is the first and foremost to advance the electromagnetics frontiers. We've been around, this is the 76th year of the society, and you'll be part of the society once you become the member of the society. With that, I'll hand over back to Mo as well as to Gopi for the main topic of presentation.
Gopi, I'm going to pass it straight on to you.
Okay, thank you. Let me share my screen. Can you see it?
Yes.
Okay. So, welcome everyone to this talk. So, what we planned for today is we would like to go through the antenna design life cycle, possibly with some examples. I don't prefer to just go through the slides. I would prefer to have some live demonstrations to keep it interesting. So for a couple of examples, I also plan to have some live demonstrations so that you can see how you can design antennas and do the antenna placement analysis using the software tools that are available from Altair. So first, we'll start with some basic introduction to antennas. I don't plan to take much time for the introductions because you are all from the EM background. Then we'll look into the antenna design life cycle. So once we look into the antenna design life cycle, that is where I want to do some live demonstrations where we can follow two different approaches for antenna design. Okay, if you already have some pre-built antennas and made a library of them, you can always reuse from the library. Or if you want to start from scratch, then you can obviously, based on your knowledge in antenna design as well as doing some literature survey, you can design a new antenna. Okay? So we'll try to demonstrate both the approaches. And optimization is built into the FECO software, and it's very useful when you're trying to design an antenna or do the antenna placement analysis to pick the right location to place the antenna. So we will go through that antenna design optimization process as well through another live demonstration. And after that, I can just quickly look into the different solver technologies available within the FECO software for both antenna design as well as the antenna placement analysis. And there are a lot of student resources available that will be extremely beneficial to all the students. So we'll look into all the different resources available from the Altair side that can be useful as well. So to start with, as you all know, antenna is nothing but a device to transmit or receive electromagnetic energy. The antenna is basically the eyes or the ears of any communication system, meaning there won't be any transmission or reception without an antenna. And nowadays, you see like antennas are everywhere. We are surrounded by them because of the way we operate these days using phones or any other electronics. It's hard to imagine the present day lifestyle without antennas. So what would be a typical design process when you're trying to design an antenna? So we basically start with the design requirements or the specifications, like the frequency of operation, the required gain, etc. And based on the antenna design engineer's experience as well as the requirements, one can pick an antenna from an existing library. Let's say they are maintaining a library of all the previously designed antennas, or you can do some research by reading about the suitable designs and come up with a new design. Okay? And whenever you start, the initial design may not meet the specifications straight away. So it would be an iterative process to fine-tune the design, either manually or using built-in automation tools in software tools like FECO. And after such an iterative process, you will have the final design that meets the desired specifications. So before we jump into the design process, either by picking something from the library or starting from scratch, I want to first give a basic introduction to Altair FECO, which is a software that can be used to design antennas as well as do antenna placement analysis. Okay. I don't want to take much time on introducing the software, so I just have 4 slides here. So FECO, it's a global leading electromagnetic analysis software suite that offers multiple frequency domain solvers as well as a time domain solver. And all these different solvers are truly hybridized in FECO, meaning when you're trying to solve a problem, part of it can be solved with one solver and the remaining part can be solved with a different solver in FECO. Okay? And because of all these different solvers within one single software, it's widely used in many different industries. It's not aimed at any one specific application, so it's a broad generalized software suite. Now, when it comes to the solvers available in FECO, as you can see here, almost all the popular EM solvers are available within FECO. So by default, if you don't specify to use any solver in FECO, it will always use method of moments. So that's the default solver. But apart from method of moments, FECO also has finite element method, finite difference time domain, adaptive cross approximation, multi-level fast multiple method, physical optics, ray launching geometrical optics, or which is also called shooting and bouncing rays method, as well as uniform theta of diffraction. Okay? And if you see those bidirectional arrows, not only having these solvers, they are hybridized. Okay? So a single problem can be solved with multiple solvers. Okay? If, for example, if you are doing antenna placement on a large platform, so for the antenna part, you can use method of moments. For the platform part, you can use one of the asymptotic methods. Okay? So if you look at so many different solvers, typically the question that we get most often is like, okay, what are the solvers that are used for antenna design, as well as what are the different solvers that are used for antenna placement analysis or the in situ analysis. Okay? Of these solvers, the bottom ones, those are full wave solvers, meaning There are no approximations involved. So the full wave solvers are typically recommended for antenna design. So method of MEMS or finite elements or finite difference time domain, or even MLFMEM, depending on the electrical size. But when you're doing antenna placement analysis, depending on the size of the platform, you can use either the full wave solvers or the asymptotic solvers, meaning the top ones, physical optics, RLGO, or UTD. So MLFMEM, you can think of it like something in between the full wave solvers and the asymptotic solvers. It is a full wave solver, but because it's extremely useful for electrical large structures, it's mostly always described along with the asymptotic solvers. Now, when you want to use the software suite for designing antennas or for doing antenna placement analysis, one of the advantages of this particular software suite is it comes with a huge library of antennas as well as platforms. Okay? And these antennas, they are fully parametric, meaning if you pick a base design and if you want to fine tune it or optimize it for any given specifications, you can always do it because it's fully parametric. Okay? You can pick these antennas from the library and add to the existing designs, or you can just start from scratch by picking something and specifying like the frequency of operation and all that. Okay? And once you select a design and add it to your existing project, you can modify different aspects of the design as well, including frequency or the dimensions, the solution method that can be used, the output quantities of interest. And if the base design is not meeting the desired specifications straight away, then you can also fine tune it by doing optimization. And optimization is built into the software suite. Okay? So there are 5 different optimization algorithms that are available within FECO. Simplex particle swan optimization, genetic algorithm, adaptive response surface method, as well as the global response surface method. Okay. So of these 5, I would say like simplex and ARSM, those are local optimizers, and the other 3 are global optimizers. Okay. The main difference would be like depending on the starting point when you start your optimization process. In a search space, there could be one global minima, but many different local minima. So if you're using a local optimizer and start close to a local minima, it will converge to the global minima. Whereas the global optimizers, irrespective of where you are starting, they will eventually converge to the global minima. Okay. Not only optimization, if you just want to do some parametric studies to understand the basic nature of a particular design, it is possible to do parametric sweep also in FECO software suite. There is a built-in macro for that. So that is the basic introduction to the software. Now coming to the antenna design life cycle. Okay. So as I explained, given the specifications, once you have the specifications, typically if you already maintain a library of previous designs, then you can pick from the library and improvise on it. Or you can do some literature search, look for some ideas from the literature and start building your own design from scratch. Okay? So there are 2 different approaches. Okay? So I will try to present examples for these 2 approaches. Okay? The first one would be picking something from the component library. Okay, so this is an example of a blade antenna for VHF aircraft communications. Okay? So the typical operating frequencies for VHF aircraft communications would be 118 megahertz to 136 megahertz. Okay? So you can see the antenna design as well as the radiation characteristics and the impedance characteristics here. Now, once you have an antenna, so antennas usually they don't operate in isolation. They are placed in their working environment. So apart from the antenna design, the antenna placement analysis is also critical. Okay, so how that antenna performs in its working environment. Okay? because this is an antenna for aircraft communications. So you can place the antenna on a platform like an aircraft and see like how the antenna is behaving when you place the antenna in its working environment. Okay. So this particular antenna, when you place on a large aircraft, because of a larger ground plane, some characteristics will change. So you can see the slight deviation in the radiation pattern of the original antenna and the antenna on the aircraft, as well as the reflection coefficient. It is still within the desired operating frequency range. So in this particular case, we may not need to change anything. But in some cases, because of the working environment, the antenna impedance characteristics might change. Then you may need to like fine tune or re-optimize the design, taking the environment into account. Okay. So let me do a live demonstration for these antennas. Okay. So to demonstrate how you can use the FECO software suite to pick a design from the library, let me just open a new interface. So this is how the FECO software suite looks like. When you look into the component library, so this is where you see all the different antennas as well as the different platforms that can be used to do the antenna placement analysis. Okay. Now, for our application, we need a blade antenna. So I can pick a low profile blade. Okay. And once you pick a particular antenna, there is some description available. So that will help to understand some basic characteristics of the antenna. And here, because FECO is not a single solver tool, it will also describe like which are the different solvers that can be used to analyze a particular antenna that is selected. Okay. If you go to next, this is where you can specify the frequency of operation. Okay. So let's say I pick a frequency of 125 megahertz. Okay. And you have an option to pick which solver you want to use, as well as you want the model for a single frequency or you want for a frequency sweep. Okay, let's say I want a model for a frequency sweep. And if you already have a platform and you are trying to add an antenna in a model with a platform, you can choose the option to align the antenna with the platform. Or if you're just starting with the antenna design itself, you don't need to align the antenna with respect to anything because there is nothing present. Okay? So if I click on create, so you can see it will automatically create the antenna for me. Okay? And if I expand the variables list, you can see this antenna is not built using like hard numbers. Okay? So if I open any of the geometry primitives, so you can see the design variables are used to specify the dimensions of the antenna, meaning it's a fully parametric design. And you can see all the different design parameters that are used in defining the shape and size of this particular antenna. Okay? And if you want to change any aspects of this design, you can simply update the values of these design variables. And when you have a parametric design, it becomes easy to set up optimization. Let's say the initial design is close, but not exactly meeting the specifications. Then you can set up optimization. And optimization is built into FECO. So if I go to the request tab, so this is where you can see when you add an optimization search. So you have an option to select a different optimization algorithm and then set up optimization to fine tune the design for the desired specifications. Okay. And when you're looking at like optimizing for any specification, so these are all the different output quantities with respect to which you can optimize a given design. You can optimize the antenna for some impedance characteristics or for some radiation characteristics, or if you have let's say an antenna array or some kind of like MIMO setup, or you can also optimize with respect to the S parameters. Okay. So here, once you have a base design, and let's say we don't want to spend time in like running the model and like setting up optimization and all that, but if you want to place this antenna on a platform, then if I go back to the library, there are also several different platform models available inside the software suite. Okay? So there is the car, this is an helicopter, and there would be an airplane. Okay, so depending on which type of platform you want to do the analysis, so you can pick one of the platforms that are available within the software suite, or if you have your own platforms, then you can obviously import into FECO. You can import into many different CAT formats. So here, this particular antenna, what I did is I took this antenna and I placed it on an aircraft because the antenna that we pick, the blade antenna, is basically for VHF aircraft communications. Okay? When I place this antenna on the aircraft, previously when I look at the antenna by itself, I have a small ground plane, but once you place this on a large aircraft, the larger aircraft body itself can act as the ground plane for the antenna. And for that reason, because there is a larger ground plane, you can see there is actually a slight improvement in the impedance characteristics. Okay? So if you look at the reflection coefficient, it's improved even further within the desired frequency band, even though the center frequency shifted, but still it is within the desired frequency band of 118 to 136 megahertz. Yeah. And if you look at the radiation characteristics, so this is the antenna by itself. And when you place this antenna on the aircraft, so this is how the radiation pattern looks like. If I hide the radiation pattern and zoom in, so you can see if you have the blade antenna at the bottom of the aircraft. Okay. Okay. And when you look at the radiation pattern and compare with the antenna in isolation as well as the antenna on the aircraft, you can see the blue curve is the antenna by itself. Sorry, the green curve is the antenna by itself, and the blue curve is the antenna on the aircraft. Okay. For this VHF aircraft communications, typically we want the transmission along the horizon. Okay. With the larger aircraft body acting as the ground plane for the antenna, the radiation pattern in fact broadened. So you can see in the broad side the change in the radiation pattern, which is actually beneficial in this case. Okay, so even though there is a slight change in the radiation pattern when the antenna is on its own compared to antenna on the platform, the radiation pattern on the platform is what would be beneficial for the VHF aircraft communications. So this way, you can always do like a basic antenna analysis, or if let's say the desired antenna is not meeting the specifications, then you can set up optimization, fine tune the design for the specifications, and then do an antenna placement analysis. So when you do the antenna placement analysis, let's say you need to make some changes with the platform, that is also possible. Now, in the beginning, I said like FECO is not a single method tool. There are like many different methods available within the software suite. Okay, and by default, when you don't specify to use anything in FECO, it uses method of moments, right? So here, when the antenna is on its own, because of the electrical size, it was just method of moments. But when you're doing the antenna placement analysis, you have a larger aircraft, right? So when the electrical size of the antenna grows, And obviously, we want to explore the other options in FECO, both for the time as well as the resources. Okay, so if you use the same method, let's say method of means for any electrical size, of course you can definitely solve, and method of means is a full solution which will be very accurate, but you may need a lot of memory as well as you may need to wait a long time for this solution. Okay, that's why here we changed the solution from the default method of means to the multi-level fast multiple method when we had this larger platform model available. And MLFMM is also a full solution, so there are no approximations involved. It's a very accurate solution numerically, so it's very good. So let's say the aircraft is too big. We are going even further high in frequency into the gigahertz range, where the aircraft might become like thousands or hundreds or thousands of wavelengths in size. That is where we can use the other solvers in FECO, like physical optics or UTD. Yeah? But what I would recommend is when you're just designing the antennas by themselves, use one of the full-wave solvers like method of means or finite elements or finite difference time domain. And when you're doing antenna placement analysis, start with MLFMM. And if you're running out of resources with MLFMM, then you can explore the other options like the asymptotic solvers of physical optics, RLGO or UTD. Okay. So this is one example where we are picking an antenna from the library and using it for the desired application, which is the VHF for aircraft communications in this case. Okay. Let's go back. Now, instead of picking something from the library, let's say there is nothing in the library that is suitable for the desired application. Okay? Then the next option is you need to come up with a novel design on your own. Okay, so based on your experience of designing antennas, you can definitely design new types of antennas, but it's a common practice to do some literature search to look for any ideas in the literature to come up with some new designs. Okay? So that is what we will try to demonstrate using this second example. Okay? So this is a dual port antenna for LTE applications. Okay? And here, if you see, this is an antenna with 2 ports. So basically, it's all connected. A single antenna design will act as 2 different antennas. And because of the orientation, by default, it will have isolation as well, because one arm is orthogonal to the other arm. So there will be like some natural isolation because of the 90 degrees orthogonality between the 2 antenna arms here. Okay. And it's not bulky because there is no physical separation between the 2 arms. Okay, so it's basically 0 for separation. Okay, and we are also not using any additional neutralization stubs or hybrids to provide isolation or to provide matching here. Okay, so that's another advantage of this type of design. Okay, but if you want to use this particular design for an application, and let's say the application at hand is an antenna for mobile phone. Okay, so we want to design an antenna for mobile phone LTE applications. Okay, now if you look at the thickness of the substrate, it's approximately 1 centimeter, which would be too bulky given the thickness of the present day handheld devices. Okay, so we need to reduce the thickness. So if you reduce the thickness, then obviously the impedance and radiation characteristics would change. So we need to come up with a new design. Okay, basically we will need an electrically small antenna that can fit within the handheld electronic device. Okay, and because I said like an electrical small antenna, so what would be an electrical small antenna? So it can be defined using this parameter called Ka. So if that value is less than 0.5, it's classified as electrical small antenna. So this is from Dr. John Volakis, where K is the wave number and A is the radius of the minimum sphere that encloses the antenna. Okay, so we need an electrically small antenna that can fit within the handheld electronic device. Okay, and the frequency of interest is 2.6 gigahertz LTE frequency. So at this frequency, the wavelength would be 11.5 centimeters. So the Ka would be approximately 0.5. So that is the size given to us, and we need to come up with an antenna design that fits within that size. Okay. So following the idea from the literature, so where we have a PIFA, inverted PIFA. So sorry, it's a PIFA. We can use that idea to come up with an antenna design, but improvise on top of it. Okay? So in that design from the literature, it's not a symmetric design, but we are trying to come up with a new design, which is perfectly symmetric, so that the antenna characteristics will be identical for both the radiating elements. And because of the orientation, so the 90 degrees separation between them, so there is a spatial separation. So obviously that will help with the isolation between the antennas. Okay? But if you take this design and try to analyze it, the initial design, obviously, even though the two arms are connected to each other, there is a good isolation, less than minus 10 dB, but the matching suffered. So we need to optimize this design to improve the matching. Okay? At the desired operating frequency, the LTE frequency band of 2.6 gigahertz, we want better matching as well as isolation between the two elements. Okay? So that is what we did here. So this is the typical dimensions of the antenna. So this is an FR4 substrate with a thickness of 5 millimeters, the dielectric constant here. Okay. And when we look at the wave number, so it's approximately 0.05. So overall, the size of the antenna should be less than 0.5. Okay. And our antenna here, this is 17.8 millimeters. So if you take that and go with this Ka parameter, so it's less than 0.5. So it is classified as an electrically small antenna. Okay? That is what we need that can fit within a handheld mobile phone. Okay? Now, when you compare the initial design with the optimized design, so obviously within the operating frequency, we have both S11 and S21 less than minus 10 dB. Okay? And at this 2.6 gigahertz LTE frequency band, typically the bandwidth is 40 megahertz. So for the entire bandwidth of 40 megahertz, both S11 and S21 are less than minus 10 dB. So we have an antenna that is matched as well as at the same time providing good isolation between the two arms. Okay. Now this particular antenna, it can be used in different configurations because we have a single antenna with the two different arms, each arm acting as an antenna on its own. So you can excite one arm at a time, or you can excite both the arms at a time. When one arm is transmitting, the other can be receiving. So these are the three different operating configurations for this design. So when both of them are excited, or one is excited, the other one is matched, so it's receiving, or when both of them are receiving. Okay. Now, when you design this antenna, so this is the initial design, but it's not going to be operating like this, right? It needs to be integrated within a mobile phone. Okay. So let me stop here for a moment and go back to the FECO models. Okay. So this is the initial design, okay? But I can't take this entire antenna and fit it inside the mobile phone. Okay. So thickness wise and all that, it fits within the mobile phone, but the substrate, that's too big. So I have only a small space at the corner of the mobile phone to place my antenna. Okay. Then what we did is we took this and we place it on a ground plane where we remove all the substrate. So because of the reduced size of the substrate and as well as the larger ground plane, now the characteristics of the antenna changed. So we re-optimized the design. So once we re-optimize this design, then this is integrated into the mobile handset. And now we analyze the performance of the antenna along with the handset. Okay, so there is a battery, there is a screen, and you have the antenna. So not only analyzing the antenna integrated into the handset, you can also go a step further, put it next to a human phantom and see how the antenna behaves. Okay, so that is what we did. So going back to the slides. So this is the radiation characteristics of the antenna integrated into the handset at the 2.6 gigahertz LTE frequency. So we have a nice radiation pattern. And when it is placed next to the human phantom, you can see once again have a nice radiation pattern along the horizon. Okay. But whenever you use the mobile handset, you either use it inside an indoor environment or in an outdoor environment, right? So not stopping at the antenna design itself, you can go a step further and do some channel capacity calculations in different environments as well. Okay. So this is the indoor environment. So if you have an antenna at just one corner of the handset, then you have like a 1x2 MIMO configuration, where on the handset you have two antennas, where on the transmitter side you have, let's say, one antenna. Or when you place this antenna on both the corners, then you can have like a 2x2 MIMO configuration, and you can see the difference between the channel capacity when you have like a 1x2 MIMO configuration versus a 2x2 MIMO configuration. Obviously, when you have a 2x2 MIMO system, you'll have improved channel capacity. So this is the indoor building in which we did the analysis. Okay. So this analysis is done in a software called Altair WinProp. Okay. So when you install FECO, actually you are installing both the FECO and WinProp at the same time. So it's not a separate software. It comes with the FECO. It's typically used for network analysis. Okay, so you can use FECO for designing antennas, but when you want to check the performance of those antennas in the environments like indoor or outdoor environments, you can do that using WinProp. Okay, so this particular talk today, it's focusing on the antenna design and optimization, but you can have a dedicated session focusing on the network analysis part of in the indoor and the outdoor environments. So this is the indoor environment. You can do a similar analysis in an urban scenario. So this is a city landscape, and as you are following a particular path, you can see how the channel capacity is. So on the left side, this is 1x2 MIMO configuration, and on the right side, this is a 2x2 MIMO configuration. Okay. So this way, you have a complete workflow using the FECO software suite. You can start with the basic antenna on its own to initially come up with a base design. So once you have a base design, you can start building on top of it. In this case, we added the bigger ground plane of the mobile handset, and then we added the other parts, the LED screen as well as the battery, and checked like how the antenna is performing. And then we placed it next to a human phantom because that's how the handset is typically used. And also, we checked the channel capacity in the typical working environments like the indoor as well as the urban environments. Okay? So this way, we have a complete workflow starting from the base design to all the way to the network analysis. Okay. So I told you that whenever you start with a base design, you can obviously improve on the base design to set up optimization, right? So let me demonstrate that optimization process using another example. The LTE antenna, if I can demonstrate the optimization process using that one as well, but it has more than 10 different design variables, and because of the size with the handset and everything, every iteration will take a lot of time. So instead, I just want to demonstrate the workflow using a simpler model which won't take a lot of time to run. So this is a printed patch, obviously for GPS applications. So we're trying to design an antenna for the 1575 megahertz GPS operating frequency. Okay? Now, when we have the base design, it is not exactly operating at the desired frequency. Then using the built-in optimization in FECO, you can fine-tune the design to meet the desired specifications, okay? To shift the resonance to the desired 1575 megahertz. Okay? So let me demonstrate that as well. So this is a slotted patch. Now, for this particular slotted patch, if you want to fine-tune this design, obviously the size of the patch can be one design parameter. Then the slot length can be another parameter. The slot width could be a parameter. The placement of the feed could be another parameter, as well as the distance of the slots to the edge. That could be another design parameter. Okay? Now, using all those different design parameters, we set up optimization. Okay. So as I said, like you can, to set up an optimization process in FECO, you can simply click on add search and pick which operational algorithm you want to use. In this case, I use the global response surface method. So once you create, it will be added. The search, optimization search will be added. So once the optimization search is added, the next step would be like defining a goal. So here, the goal could be either the impedance goal if you are trying to like improve the matching or shift the resonance to the operating frequency, or let's say you are trying to improve the radiation pattern or gain, and you can add a far field goal. You can also add multiple goals if you want to optimize the design for multiple parameters at the same time. Okay, but to optimize the design, obviously, like some aspects of the design should be modified, and that is what you add under the optimization parameters. Okay. So if I open the optimization parameters, so the feed position, the patch size, the slot length, the slot width, as well as the distance of the slots from the edge. So those are the different design parameters that I selected to fine tune this design so that the resonance will be shifted to the GPS operating frequency. And for the goal, that is what I specified. So I'm trying to optimize the reflection coefficient. I'm trying to make it equal to, let's say, 0.1 at the 1575 megahertz frequency. Okay. When you want set up optimization, so what you do typically is when you run an analysis, instead of running FECO solver, you run opt-FECO. So when you run opt-FECO, obviously, initially, let me open the design parameters. Whatever start value you gave, it will start with those values for the design parameters. But from the second iteration onwards, depending on how or which direction the optimization is going on. So once it evaluates the goal, then it will pick the next values for the next iteration and evaluates the goal function. And depending on the goal function value, so it decides whether it needs to, if it is moving in the right direction, then it will try to fine tune the design variables so that it can converge onto the goal. If it is going in the wrong direction, then it will try to pick completely dramatically different values. Okay, so it's an iterative process, but it's built into FECO. So once you set up a range for your design variables and give a start value, then obviously the software will do its job. Okay? And this is what happened here. Okay? So we have the initial design that once we set up an optimization goal to fine tune the reflection coefficient, then we are able to get an optimized design where we have a perfect match when S11 less than minus 20 dB at the 1575 gigahertz, 1575 megahertz GPS operating frequency. Okay. And if I look at the radiation pattern. Okay. So once we have the base design, say if I want to add, let me save as. I can also look at the 3D radiation pattern of this design. Just for the sake of time, let me run it at 1575 megahertz. I picked this example because even for live demonstration, it won't take much time to run, a few seconds. That's the main idea behind picking this example for demonstration, rather than like showing a live demo with that LTE antenna. If I open post-FECO, you can look at the radiation characteristics as well. Okay. So here for quick analysis, I chose an infinite ground plane with substrate, but obviously once you have more or less the base design that meets the requirements, you need to add a finite substrate with a finite ground plane and do a finite analysis and maybe some additional tweaking if the size of the ground plane is impacting the performance of the antenna. There might be some resonance shift, but if it is still within the operating frequency band, you should still be good. Okay. So that's how you can use the built-in optimization within the software suite to pick a base design and improvise on top of it, either manually or by using the built-in optimization within FECO. Okay. Now coming to the different solvers, if it is for the antenna design itself, then obviously I will always recommend to go with the full wave methods like method of means, finite element method, finite difference time domain, or adaptive cross approximation, even MLFMM, depending on the size of the antenna. But once you have an antenna design, and if you want to test the antenna in its working environment, like placing the antenna on the platform, now more or less in majority of the cases, the platforms will be electrically large. So you can use the methods like MLFMM or any of these asymptotic methods like physical optics, large element physical optics, RLGO or UTD for the antenna placement analysis to understand how this antenna will perform in its working environment. Okay. So just a quick overview on these different solvers. So for the antenna design, as I said, you can use method of means, FEM or FDTD. So when it comes to FEM, so this is the default solver in FECO. So when you don't specify to use anything, FECO will always use method of means, and it's a fully featured implementation. Okay? Meaning you can use it with infinite ground planes and substrates, or you can use it with just finite 3D arbitrary geometries with dielectric substrates. Okay? So all metals, wires, combinations of metals and wires, dielectrics, dielectric coatings, impedance sheets, they're all supported with method of moments. And even there is something called adaptive cross approximation, which is an acceleration of method of means. So if you have a complex model with a dense mesh, but it is electrically small, then you can definitely use ACA to reduce the computational resources. And method of means also supports higher order basis functions. So if you have a simple design where you don't need a dense mesh, but let's say it's electrically large, then obviously you can, instead of going with a fine mesh, you can coarsen the mesh, use higher order basis functions to solve the same problem. That would save for the computational resources. And depending on the application, if you're trying to solve it extremely low frequencies, then the model or the problem might become quasi-static. For those cases, method of means also has something called low frequency stabilization, So there, apart from the default RW basis functions, FECO will use additional loop star basis functions to add extra stability to the solution. So you have a converged solution. If the problem or the antenna model is simple, I would recommend to use method of means. But let's say you have an extremely complex antenna design with many different dielectrics, then method of means will start taking more computational resources, because when multiple dielectrics are involved, even like if there are metals versus there are dielectrics, the number of unknowns are automatically doubled for method of means when there are dielectrics. So for that case, when you're dealing with complex geometries including dielectrics, I would recommend to use finite element method. And it's easy to switch between different methods in FECO. They're all available within the same software suite. And traditionally, it's beneficial to use finite element method with inhomogeneous materials, and it's extremely memory efficient compared to method of means, and it can have unstructured mesh. So when you have complex geometries, sometimes it helps to mesh complex shapes. But some thing to watch out for, like the numerical dispersion, if there is some inaccuracy, and as you are going through an iterative solution, that can add up. So there is a problem of numerical dispersion. And with method of means, you are just discretizing the given geometry and nothing else. But with finite element method, you always enclose the geometry in an air box and discretize the entire volume. So because of that space discretization, when the problem is electrical large, the air box would be huge. So it's a disadvantage. But traditionally, it's memory friendly. So it's still okay to use finite element method even with electrical large structures, unless you need extremely dense mesh. And the finite difference time domain between method of means, finite elements, and finite difference time domain, I would say FDTD would be the most memory friendly solver. But time depends on the time step, which in turn depends on the finest mesh element within the entire model. Okay, so it's extremely memory efficient. And whenever you're trying to solve, like let's say wideband antenna models, so instead of using a frequency domain solver where at every frequency it requires the same amount of memory and time, if you're solving in time, then inherently you're solving over a broad frequency range. So that's another advantage. So whenever you have complex models or like extremely wideband models, I would recommend to go with finite difference time domain. And when it comes to the antenna placement, then always start with MLFM, because it is a full wave solver. So just like the previous three solvers, it is also a full wave solvers, no approximations involved. You can also think of MLFM like an acceleration of method of moments. Okay? So where different unknowns will be grouped, and the interactions will be between these groups rather than an unknown to unknown interaction in method of moments. Okay? So just as an example, a problem that takes close to a gigabyte with method of moments can be solved with like 10 gigabytes using MLFM. Okay, that's how much you can save if the problem is well suited for MLFM. So the problems are well suited for MLFM if they are electrically large. Okay, so as a rule of thumb, if the problem is more than 5 wavelengths in size, then start using or start taking advantage of MLFM. Let's say you have finite resources. Okay? You are not able to solve the problem using even MLFM. So you don't have enough resources to solve. That is when I recommend to use these asymptotic methods like physical optics, RLGO, or UTD. Okay? Because there is no other option to solve with any of the full wave solvers. That's when you can solve with these asymptotic methods. They are extremely memory efficient, so they take a lot less memory and time compared to any of the full wave solutions. Okay? With physical optics, so unlike any of the full wave solver, where with method of means you are solving for currents, with MLFM you are solving for currents, with finite elements and finite difference you are solving for fields in the Maxwell's equations. Here you don't directly solve Maxwell's equations like the traditional way when you are using the asymptotic methods, but with physical optics, you still solve for surface currents using the simple 2n cross H approximation. That's how it can save both memory and time. But in FECO, it's by default hybridized with method of MEMS. So when you're doing antenna placement for the antenna part, which is the radiating structure, it will be treated with method of MEMS, but the larger platform, that would be treated with the physical optics. Okay? So all the asymptotic solvers, physical optics, RLGO, or UTD, they are applied on the geometry. So you select all the surfaces of the platform and specify to use one of those asymptotic methods. And RLGO, so when you're using physical optics, so you are still solving for scattering. So for antenna placements, it's extremely useful. But if you have a problem where you need to take into account transmission through the geometry as well, for example, like a dielectric lens antenna or radome, that's where you need a solver like ray launching geometrical optics, because with physical optics, you don't take into account the transmission through the structures. Okay? Whereas RLGO, it can account for the transmission through the structures. Okay? And as I said, it is also hybridized with method of MEMS. So the source part or the radiating element part will be treated with method of MEMS, but the larger plot, whether it is a reflector or a dielectric lens or any other larger platform, that can be treated with RLGO. Okay? And same thing with UTD also. Okay? So when you have a platform that can't be handled even with physical optics, let's say you have hundreds or thousands of wavelengths in size, a platform like a huge ship, there you can save a lot of resources by switching to UTD. Because of the ray tracing approach, it takes a fraction of resources compared to any of the full wave solutions. Okay? So that's a quick overview on the different solvers. I didn't want to take much time on the solvers, but coming to the student resources, obviously the student edition of the software, it's available for free, no cost to all the students. So you can register on Altair website and download the student edition and use the software. And when you install the software, there are tons of examples that come with installation. But there are also a lot of e-learning resources, some basic applications, some main solving features, as well as basic introduction to the software. Okay? You can take advantage of all these different self-learning modules as well. And we also have something called Altair Community, which is a great resource for discussions. Okay? So if you have any questions, you can post questions, and not only posting questions, but you can interact with other community users to exchange ideas. So I would definitely recommend, once you register for the Altair One account, then you automatically have access to the community page. So you can involve in the discussions. And so when you install the software, it comes with a lot of examples that, and as well as the documentation for all those examples. But I would also recommend this particular book co-authored by Dr. C.J. Reddy. We all know Dr. Reddy. I don't need to give any introduction, but this is a great book where all the different antenna examples that are used, those are solved using FECO. So you can always reproduce those examples using FECO. So I think that is all I wanted to cover today.